use. And then what I will also do is, since I'm going to be not imposing rational expectations equilibrium, I will look at what's called a temporary equilibrium, which is basically says that given the expectations, which I denote by actually, sorry, there's a change in the time index pi, and these are about the future. And then given those in the earlier equations, we have the aggregate demand, which is the consumption function plus market clearing, the Phillips curve. And then we had these two asset dynamics, bonds and money, but they, under Ricardian assumptions, they evolve independently of what's happening. They don't depend on consumption and so forth. So, I'm sorry, they depend on, but they don't influence consumption decisions or production decisions. And then there's an interest rate rule. So we have some state variables here as well, but the setting is this kind of one directional dependence. And then for the expectations, I will explain it more in a moment, but I assume something what's called steady state learning. I'll come to the details later on. But it basically says that for all future periods, we have these given expectations in temporary equilibrium, and so we have an aggregate output equation, which says that output depends on, is basically equal to the government purchases plus what you have as the consumption function we had before, the private, what goes to the private sector of the purchases. And then I've done one more assumption, which is that they know the interest rate rule. One could do away with that, but simplify. This will keep us lower dimensional. I can do some geometry a little bit later on. And then we have a Phillips curve. Remember, I had that K function earlier on, and I'm just going to invert that Q function, and then I have an inflation depending on expected output and expected inflation for the future. Now let's start with steady state. We can be fast here because we've already seen the story, which is that suppose we impose steady state. So these are constants over time, these expectations and other variables then as well. Then there are two steady states, as I said, and with the low steady state being having a lower inflation rate. And then if we do the learning process and require that it converges somewhere, the usual steady state, the pi star, is something what we call locally stable under learning. Locally stable means the usual mathematical meaning, which says that if you start nearby, you will converge to that fixed point. And the low steady state is not stable and locally stable under learning. It's unstable, but it has an important property here, which is it's a saddle point. We will see that it plays a major, that property is an important one for the future. Anyway, so let's get to the details of the expectation. So the idea is that agents somehow form expectations. They have relatively incomplete information, so they don't have rational expectations. They obviously know their own utility and production parameters. They know the government budget constraint because they read the budget book of the country. But they do not know much about the other agents. In fact, we assume that agents are identical, but they don't know that they are identical. Because otherwise, if they knew, it would be a different story if they knew that everybody is the same one. Very different story. And then for the expectation formation, in this learning approach, what is assumed that agents are like econometricians. So they've gone to a business school or a university economics training and done some econometrics. And they estimate and economic forecasting model on the basis of the data they have, an econometric model, and then make forecasts given that estimated model. And as they get new data, they revise their forecasting model, estimate it again, and update the expectations. So that's part of the dynamics. This is the learning process. It's part of the dynamics, and we will assume then the estimation is going to be done least squares and so forth. Simple things. One could assume more fancy things like nowadays this computational intelligence is very popular. And actually the least squares algorithm written in a recursive way is a very simple stochastic recursive algorithm. So it's in some sense a predecessor for some of the more complicated things. But there are papers which do these more complicated learning formulations as well. But that's kind of new in the literature. So here's the steady state learning, which is, this is least squares learning applied to estimating a constant. So that's the simplest forecasting model you have. You think that inflation is going to be constant in the future, or output is going to be a constant in the future. Again, this is the simplest thing to assume. It is, it's, for any more complicated forecasting, it's an important part of anything more complicated, because when you have a forecasting model, you have an intercept term. And for estimation of that, this is crucial. So that steady state learning is actually, it's simplified somewhat, but it's basically estimating the intercept anyway. And one could have then other things here. And the trouble here is that I'm not going to impose explicit shocks, except sometimes say that there's a shock has happened. And then I cannot have a more complicated model of estimating an intercept and a lag, for example, on these other variables, because you're going to run into multicollinearity problems in a non-stochastic model. If one could have stochastic models, and fine, that has been done. So anyway, this, if you have steady state learning, then you can approximate the dynamics. This is an approximated dynamics by two differential equations. How the expectations of output evolve, and remember that's the Phillips curve G1. That was the notation for it, and how expected inflation. This is the Phillips curve. This is the output equation part of it. Now, this something called instability is one which has been used a lot in the literature. And it's an old technique that were developed in the late 80s, since we basically started the collaboration. George Evans and I have worked a lot on this. The nice thing about it is that we can do a lot in geometric terms if we have two differential equations. We can do phase diagrams to illustrate the dynamics. And that's why I've been doing all these simplifying assumptions, because we can get a nice handle on what might happen by looking at this simple case. So, okay, so let's get to the phase diagram. We put a lot of parameter values so that we can put it on a program. Let me not talk about these in different. And here's what the phase diagram, what you get. So we have expected inflation on the horizontal axis, the expected output on the vertical axis, and this is the two instability differential equations, their dynamics. And one thing I forgot to say is that dynamics is in something called virtual time. The real time is discrete. This is a continuous time. It actually has a sort of a nonlinear relation to the real time. But it's basically adding moments together, so you have it more tightly when t gets large. And so what's happening here is that this here is, notice that I've tuned it so that there's a 2% inflation bracket. So inflation 1.02 means that that's where the gross inflation is 2%, where the net inflation is 2%. And so here's going to be the targeted equilibrium. And then here we have, that depends on the discount factor, but it's basically, it's somewhat below 1, which is on the deflationary side. Here's the low equilibrium. We've got the two yellow curves and then the blue curve here. I'll explain this complicated curve in a moment. So these are what you call the isoclenes in the differential equations, where one of the derivatives is going to be 0. You notice that from the arrows, what's happening here is that, like here, they're going like this, or like here, the dynamics are going to go like that. So we have the two steady states, and we see the dynamics. And in particular, notice what we see is that if you are inside this complicated-looking curve here, the dynamics will, from here, they will go like this. They will start to cycle and converge to that steady state. So that steady state, as I said, it was locally stable, but that convergence is cyclical. Whereas if you're here, even if you're here that inflation is high and output is kind of high, you will eventually can get into trouble in the sense that you're going to go like this if nothing else is happening. And then you get into a region which is below the low steady state, so it's a deflation trap. And notice that once you've gotten into here, you're not going to get out unless something happens again. If nothing happens, then you don't get out. So we have a deflation trap here. And the interesting thing about this is, remember I said, those who know mathematics, I said that this low steady state is a saddle point. This complicated curve is something what's called the stable manifold of the saddle point. So, and notice that it separates the convergence to the target steady state. So this area is what's sometimes called corridor of stability. From there you get of that equilibrium. And this is the separation. It actually goes through that low steady state. And that's the sort of thing you get out of there. And so in some sense, if inflation has been very low, like 1% or so, and then if output levels are also depressed, you know, maybe the real economies are maybe somewhere around there because of the shocks. And then it's kind of delicate. Are you going to eventually start getting back with unchanged policies, or could it be that unchanged policies will take you just to eventually to the deflation trap? And that's in terms of this figure, the current concern. I'm going to just go through this I've already mentioned. So let's get to the policy.